بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Section 4.6 Graphing and the first derivative test. The aim of this section to introduce the first derivative test, which relates the concept of relative extrema of a function f and f prime. Also to sketch the graphs of function using the first derivative test. So first, what is the first derivative test? Let f be a continuous on the closed interval a to b and differentiable on an open interval a to b, except possibly at the critical number c. So, if f prime x change from positive to negative at a point c, then fc is a relative maximum. So if the derivative change from positive to negative, then we say that at the point C, the function has a relative maximum. And if f prime x change from negative to positive at C, then fc is a relative minimum. So if your function change from negative to positive, then we can conclude that this function has a relative minimum at the point fc. But if f prime x has the same algebraic sign on each side of c, then fc is not an extrema. So for example, your function is here negative, then negative. So we say that there is no relative extrema. Or it is positive, then we will say there is no relative extrema. So here, if your function was increasing where the derivative is greater than 0, then at the point C, we have, after the point C, from C to B, we have f decreasing where the derivative is less than 0. So if the derivative greater than 0 before C, then less than 0 after C, we see that this function has a relative maximum. For the other case, if the derivative is less than 0 where your function f decreasing, then after the point C, your function is increasing where the derivative is greater than 0, then we conclude that our function has a relative minimum. So for the first derivative test, we have 4 cases. If our function or the derivative is positive, so that means our function increasing, then after the point C, our derivative is negative, so that means our function is decreasing. So we said that at the point fc, the function has relative maximum. If the derivative before c is negative, then after c is positive, then we say that our function has a relative minimum at the point fc. But in case if your function before c is decreasing, then after c is also decreasing, then we conclude there is no relative extrema. Similarly, if the function or the derivative before c is increasing, then after c it is also increasing, then we conclude there is no relative extrema. So we have two relative type of relative, maximum, minimum. The maximum when the function increasing then decreasing, and the minimum when the function decreasing then increasing. Here we have a question. Can you give any example of a function where the critical number does not correspond to a relative extrema? So here it said that sometimes we have a critical numbers. We said that the critical numbers is when our function is equal to 0 or does not exist. So that will give us there is no relative extrema. We said that we have just one side. If the function has a relative maximum or minimum, then at this point the function has a critical value. Or we said this number at this point, this function has a critical value. But if the function has a critical value, that will not guarantee this function will have a relative maximum or minimum for these two cases. And we have one example of this is x power 1 over 3. At x is equal to 0, our derivative does not exist, but the function has no relative maximum or minimum at this point. So here we have guideline to sketch a graph of a function f. First we need to find the domain of f, then find the intercept of f. We have two types of intercept, x and y. Then we need to test the symmetry of the function f, if it is symmetry about the x-axis or symmetry about the y-axis. Then we need to find the asymptotes, if any. We know that we have two types of asymptote. Vertical asymptote, where the derivative or where the limit of the function when x approach to infinity or minus infinity give us a number. Or vertical asymptote, where the limit of the function when x approach to a is equal to infinity or minus infinity. Then we need to find relative extrema using the first derivative test. That first we need to find the derivative, then factorize the derivative, find the critical number where the derivative is equal to 0 or the derivative does not exist. Then we need to apply the first derivative test to each critical number, apply this to know when the function has relative maximum or the function has relative minimum. So here I rewrite this guideline so you know how to find the domain. So we have 5 steps. First one is find the domain. Second is to find the intercept, x-intercept, but y is equal to 0 and solve for x. Y-intercept, but x is equal to 0 and solve for y. Then you need to test the symmetry of f. If you want to test the symmetry about y-axis, then you need to check if fx is equal f minus x. Then that means your function is symmetry about y-axis. But for the symmetry about the x-axis, you need to test is fx is equal minus f of x. If they are equal, then that means you say that your function is symmetry about the x-axis. Then you need to find the asymptote, if any, vertical asymptote, where the limit of the function when x approach to a is equal plus or minus infinity. And for the horizontal asymptote, you need to check limit of fx when x approach to plus or minus infinity give us a. Then the last step, find relative extrema using the first derivative test. So let us see example 1. Sketch a graph of fx is equal minus x squared plus 2x plus 1. So for sketching a graph, we see that we have to go all these 5 steps. So if you see your function fx here, it is a polynomial. So the domain for any polynomial will be from minus infinity to infinity. Then the step 2, we need to find the x and y intercept. For the x-intercept, put y is equal f of x is equal to 0 and solve this function for x. So if we multiply this one by minus 1, this will give us x squared minus 2x minus 1 is equal 0. So now using the general rule to find the x value, it will give us 1 plus or minus root 2. So the x-intercept will be 1 plus root 2, 0, and 1 minus root 2, 0. For the y-intercept, put x is equal to 0 and then solve for y. So if x is equal to 0, here we'll get 0 and then 0, so y will be equal 1. Sorry for this one, so this is by mistake, y is equal 1. So the point will be 0, 1. So now checking the symmetry, we have to check the symmetry about the x-axis and the y-axis. The symmetry about the x-axis, we need to check if fx is equal minus f of x. So first we need to multiply the function fx by minus 1. So if you multiply this function by minus 1, which is minus f of x, this will give us minus multiplied by minus, it will be plus, minus multiplied by plus will be minus, then minus multiplied by plus, minus. Now if you compare x squared minus 2x minus 1 with minus x squared plus 2x plus 1, they are different. So we see that minus fx not equal to fx, so there is no symmetry about the x-axis. For the symmetry about y-axis, we need to check if fx is equal f minus x. Where f minus x, we go to the function f, replace any x by minus x. So here we have f minus x will be equal, here we have minus x squared, so it will be minus x whole square plus 2. replace x by minus x, we get 2 multiplied by minus x plus 1. So this will give us minus x squared minus 2x plus 1. If you compare this one now with the original function, they look different. So we conclude that f minus x not equal to fx, so there is no symmetry about x-axis, there is no symmetry about y-axis. So now for the vertical asymptote, it is clear for this one it is not a rational function, it is defined everywhere, so this function has no vertical asymptote. So we conclude fx polynomial, there is no vertical asymptote. For the horizontal asymptote, we need to evaluate limit of the function when x approach to plus infinity and the limit when x approach to minus infinity. So limit of minus x squared plus 2x plus 1 when x approach to plus or minus infinity, we will take just the highest power, which is minus x squared. So the limit when x approach to infinity will be minus infinity, and the limit when x approach to minus infinity also will give us minus infinity, which is not a real number. So we conclude there is no horizontal asymptote. Now for step 5, we need to find relative extrema using the first derivative test. So first we need to find the derivative of minus x squared plus 2x plus 1. So it will be minus 2x plus 2. So now we need to find the critical number by finding f prime x is equal to 0. So f prime x is equal to 0, that's mean minus 2x plus 2 is equal to 0. So when you solve this one, you will get x is equal 1. X is equal to 1 is a critical value or a critical number since it is in the domain. So now we need to check the value of the derivative before x is equal 1 and after x is equal 1. So we'll draw this table. We have here x, f prime x, and f. We have here 1, here minus infinity, here plus infinity. So if you take any number, substitute on f prime x, substitute here. For the any number from minus infinity to 1, it will be positive. So our function here, it is increasing. Then if you take any number from 1 to infinity, substitute here, you will get it is negative. So that's mean your derivative is decreasing. Your derivative is negative, that's mean your function is decreasing. So since our function is increasing then decreasing, we conclude fx has a relative maximum at f1. So you go to the function 1, you go to the function f, you replace x by 1, so minus 1 plus 2 plus 1, this will give us 2. So the relative maximum will be at the point 1, 2. So now how can we sketch our graph using all this information? So we have the x-intercept 1 plus root 2 0 and minus root 2 0, the y-intercept 0 1. So here we have 1 minus root 2 0, is 1 plus root 2 0. We have the y-intercept here 0 1. Then for the symmetry, we have no symmetry. For the symmetry, sorry, we have no symmetry about x-axis, no symmetry about y-axis. So for the vertical horizontal asymptote, there is no vertical, there is no horizontal asymptote. Now for the relative maximum, we have at the point 1, 2, so we need here at the point 1, 2, we have relative maximum. So you have these 4 points. You have here point, you have here relative maximum, you have this one, you have this one. Then just you need to connect through these 4 points and you will get this is the shape of our function f of x.